Welcome to the intro of quantum walks. Today we'll explore this fascinating concept that lies at the intersection of quantum mechanics and network science. To start with, let's introduce you to some basics of quantum mechanics. Quantum mechanics describes the behavior of matter and energy at the scales of atoms and particles. In contrast to classical mechanics, quantum mechanics predicts that particles can exist in multiple states simultaneously and can exhibit entanglement, where the properties of two particles are correlated even when they're far apart. One of the fundamentals of quantum mechanics that would be helpful in understanding our concepts of quantum walk is the wave function. The wave function is a complex valued function that describes the states of a particle or system and gives the probability amplitude for the particle to be in a certain state or location. The probability density of finding the particle at a particular location is given by the square of the absolute value of the wave function. Okay, with these ideas in mind, let's head right to the point of our main topic today, quantum walks, a type of random walks that follows the laws of quantum mechanics. To understand this concept, let's consider a very simple example. Suppose you're standing on a grid and you can move either left, right, up, or down. In a classic random walk, you'll randomly choose a direction and move to that spot. However, it will be very different if it's a quantum walk. In a quantum walk, you will exist in multiple states at the same time and move to all adjacent spots at the same time as well. Now, let's scale this up to a complex network. Instead of a simple grid, let's consider a more complex network with nodes and edges, where nodes represents entities such as people, genes, or cities, and edges represents the connection between them. A quantum walker will exist in multiple states simultaneously, and at each step, it will move to all neighboring nodes at the same time, rather than choosing one single mode randomly. Okay, let's head to a more specific example, supposing we have a social network of people, where each person here represents a node in a network and the edges will represent their social connections. In this network, we could use a quantum walker to search for a specific person. We can start the quantum walker at a very random node and let it take a series of steps. At each step, our quantum walker will exist in multiple states and then move on to all neighboring nodes at the same time. In the case of quantum walker in the social network, the probability distribution that we mentioned earlier represents this probability of finding the walker at a given node in a network. After several steps, the quantum walker's probability distribution would be spread out across the network, reflecting the walker's quantum interference with itself. The probability distribution of the quantum walker evolves over time according to the Schrödinger equation, which describes how the wave function changes in response to the Hamiltonian of the system. In our case, the Hamiltonian takes into account of the connections between nodes and networks, and it determines the probability of walker transitioning from one node to another. It also includes a phase factor that accounts for the quantum interference between the walker states. As our quantum walker takes more steps in the network, its probability distribution gradually becomes more localized in certain regions where the quantum interference of the walker states is constructive. Those localizations allows us to find the target node much more efficiently than using a classical random walker. In fact, research has suggested that quantum walks have been shown to speed up search algorithms in complex networks exponentially compared to classical random walks. The implications of quantum walks in network science are significant, and the above is just one simple example of how it can be applied. Quantum walks can also be used for walks about routing, optimization, and other network-related problems. The potential application of quantum walks are vast, and they offer new insights into how complex systems operate and opens up new possibilities for developing efficient algorithms for real-world problems. Thanks for watching, and hopefully you find this video very interesting. For more in-depth information about quantum walks, feel free to check out the links attached in the description.